Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchats, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first 3: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested of course and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Okay, so like I said, today the lecture is going to be more a kind of a tutorial. So we are going to solve these three examples at least, and we are also going to solve this example which was from last year exam. Alright? So this came in last year exam. We are going to solve this example today together with these three examples here. So the idea is first to build the equivalent system force moment and then apply the equilibrium equations to get the results for the unknowns. Right? It can be reactions or forces in the cables. Okay? So let's start with this one here. Let's put it here. So let's start with this example. So this example was taken from the Ibler book. Statics. And what you have there is, you have this frame where you have a beam here in the top. So this is a beam here, okay? And you have also this column here. And then you have applied, the beam is as this support at A and this hinge at point B. Okay? So the supports are very important. For some reason the red is black in the whiteboard. Let me just see if... Okay. Yeah, the red is black. I don't know. It doesn't matter. Okay, so you have these supports. As we have seen, we are going to build the free body diagram. So we need basically to replace the supports with the reactions, right? So the type of supports you will have is quite important for the free body diagram. And then you have all these loads applied. So you have these 25 kilonewtons here, 35, 50 kilonewtons, and 10 kilonewtons. And you also have these 2.5 kilonewtons over there. Okay? Good. So the question is, determine the reactions at the supports A and B of the frame. Okay? So we are going to do this step by step. So the first step is always the construction of the free body diagram. So we are going to build the free body diagram of this structure. For the free body diagram, you can make a simplified. So you don't need to draw all the details of this frame. For example, for the beam, you can just say, okay, this is the beam. Right? This is the column, and this is the other beam over there. So we can make this kind of more simplified model. Now we need to represent all the external forces acting on the frame. We have this 25 kilonewtons here. We have 35 kilonewtons here, 50, and we have here 10 kilonewtons, right? Okay? And we also have this 2.5 kilonewtons. Alright, so what I did so far was I isolated the frame from the supports. I removed the supports and I represented all the external forces in the frame. Now what I need to do is I need to replace the supports with the reactions. Okay? So starting with support A. So if you look at this support here at point A, So you can see that beam is supported in a roller, right? So roller means the beam can move in the horizontal direction. You all agree with me? Yeah. So it means if it can move in the horizontal direction, there will be no reaction in the horizontal direction. Okay? So that's what we agreed last week. Whenever the body we are analyzing is free to move or rotate, it means there will not be any reaction in that direction. Okay? Only if that movement is constrained, it means that constraint is the meaning of the reaction. The reaction is constraining that movement. Right? So that's what happens here for point A. If I try to move the beam, for example, if I try to move the beam downwards at point A, that roller will not allow that movement, will constrain that movement. So it means I will have to include here a reaction at point A in the vertical direction. And that reaction is, I'm going to call it AY. You are free to call it whatever you want. But a good rule of thumb is to... Okay, so we are getting the reactions at point A. So let's call it A. But then we can have a reaction in X and Y. So why not put a subscript Y in this case? So it means it's a vertical force, right? Reaction, vertical force. Now, if we now do the analysis for support B. So support B is an hinge. So it means if I try to move that point B of my frame in the horizontal or vertical direction, that movement is going to be constrained. So it means I need to include two reactions here. I'm going to call this Bx. And this I'm going to do By. So don't worry about the direction. For example, By, I represented downwards. I could have represented upwards. It doesn't matter. Because, as we are going to see at the end, the signal of the reaction will tell me if my initial orientation was correct or not. All right? Now, we need to think as well for an hinge like this at point B. We also need to think what happens if I try to rotate the frame about point B. That hinge will allow that rotation or not? What do you think? It will allow, right? So if it allows, it means there is no resistance to that rotation. So it means no moment as reaction. All right? This is a key thing on the solution of this kind of problems. As you can see, it's not very difficult, in my opinion, of course. If you think this way, you are able to completely characterize the reactions you need to include. And the problem is that if you don't have the right reactions, it means your problem is completely wrong. So this is a critical step that you need to be very careful, okay? So that's why we are going to do some examples today to practice, and you can also practice more examples at home. There are many different books in the library you can practice, okay? All right, so the only thing we need to do now is to include a coordinate system so that we can finalize our free body diagram. So we are going to. So this is a two-dimensional problem. We can include the origin of the coordinate system at any point you want, point A, point B, or any other point if you prefer. I'm going to, for this example, to select point B for my coordinate system. So this is going to be my X direction, and this is going to be my Y direction. Is okay? All right. So that's it. So this is the free body diagram. That's all you need. Of course, the dimensions and these distances are included here in the original problem, right? So you don't need. You can put it in the free body diagram if you want, but okay. Now, next step is. So let me copy this. Next step will be now the construction of the equivalent system force moment. Okay? We can also copy this one for the dimensions. So let's put it here side by side. So we have the dimensions there, okay? So we have our free body diagram there and the original problem with the dimensions. So what we have to do now is we have to build, so I'm going to write here, we have to build the equivalent system force moment. Okay? Why do we have to do this? Because as you can see in your free body diagram, we have forces applied at different points. So we need to make an equivalent system where everything is concentrated at one single point. And that point can be any point you want. You just choose, okay? Which point do you want? Point A, point B? Point A? Okay, so let's build the equivalent system force moment at A. So, first thing is, we need to calculate the resultant of the forces. And that resultant is basically the summation of all the forces we have. Okay? So we will have... so let's do this way. What forces do we have in the horizontal direction or x direction? What do you think? Bx. Yeah. So Bx. What else? Minus 2.5. Good. Do we have anything else in the horizontal direction? No, that's all we have, right? Now, what about the vertical direction or y direction? Which forces do we have? Ay. Minus by. Yeah. What else? Good. All of this, right? That's it? So this is the resultant of the forces. And now we need to calculate the moment. So basically this is going to be the z component of the moment, right? So in a two-dimensional problem, the moments, they have only component in the z direction, perpendicular to the whiteboard. So we need to calculate the moments about point A. Don't forget, we are building the equivalent system at point A. Okay, so let's start. This 25 kilonewtons here, does it produce any moment about point A? No. What about AY? Does it produce any moment about A? No. What about this 35 kilonewton? Yeah. So that moment is positive or negative? Negative. It's going to be clockwise, right? So we can say minus. So how much is the moment? 35 times 2.4. Yeah, good. Now, this 50 kilonewtons, does it produce any moment about A or not? Yeah. How much is it? Positive or negative? So 50 times 2.4 plus 1.8, right? Which is 4.2, isn't it? 4.2. Now we have these 10 kilonewtons. Okay, also negative, right? Clockwise. So how much is the moment? So for 6, yeah, 6 is the distance. 6 times 10. Right? Do we have any other moment? For example, this force, 2.5 kilonewtons. Does it produce any moment about A or not? No? Why not? The moment, look, this force, 2.5 kilonewtons, so this is the direction of this force, right? The moment is the distance in the perpendicular direction to the force times the force. So there is a distance in the perpendicular direction to the force, right? So we should consider this moment as well. All right? Now, is it going to be positive or negative? Yeah, we are going there. By, yeah. So negative, yeah, very good. How much is the distance? 2.4 times the force, which is 2.5, right? Now, Bx. Does Bx produce any moment about A or not? Sorry? Someone is saying? It's okay? Okay, how much is the moment? Is positive? Yeah. So plus. How much is the distance? 4.2 times the force, which is Bx. Now, By. Does By produce any moment about A or not? It's positive or negative? Negative. So minus, I'm going to continue here. Minus, how much is the distance we need to consider? Isn't it? This distance. Huh? You all agree with me or not? No? Okay. Why not? Yeah, so the perpendicular distance, yes. So let's do it here. So this force, By, the direction of this force is this, right? The distance in the perpendicular direction should be this one. Isn't it? Should be this, right? Which is 4.2. So we have minus 4.2 times By. For the 2.5. So the moment produced by this force 2.5 about point A needs to be this distance, which is the distance in the perpendicular direction to the force. And this distance is 2.4, isn't it? Look here, 2.4. Right? So how much did we consider? We considered 2.4 times 2.5. It's correct. It looks correct to me. Okay? Okay, so this is the moment. Do we have anything else? Any other component for the moment about point A or not? Or this is it? It looks like this is it, right? So now, let me copy this. So this is our equivalent system force moment. Okay. Now what we need, the next step, what we need to do next? Yes.
Is there no, can you go back? Is there no reaction at the beam that's supposed to do on the beams?
Which one?
The little one.
This one?
Yeah.
What diagonal? This? Hold on. This is not a force. Is it? This is this beam here, right? This beam, there's going to be a force there, but it is an internal force. We didn't separate this beam from the frame, right? This beam, look, when we did the free body diagram there, basically I did this beam here, I did the column here, right? And I also included this inclined beam, right? There. I didn't separate that inclined beam from the frame. Okay? We are going to see in the second or third example we are going to do today. that if you don't separate the members, it means you don't put the forces. They are internal forces. Okay? So what you are saying is not a force. So this part here is this structural component, is a beam that is part of the frame. Okay? If for some reason you decide to separate this beam, for example, imagine you decide to do this. Well, you have the beam, you have the column, and you have this inclined beam, right? If you decide to take this and isolate this inclined beam from the frame, then you are basically doing a new free body diagram for this inclined beam, right? And then if you do that, you need to include for example, the forces, right? When you separate the beam from the frame, your internal forces become kind of a reactions, right? Then you need to represent. But in our example, we did not separate this beam from the frame. So when you don't separate the beam from the frame, you don't put the forces. Okay? For example, think again for the reactions. When we built the free body diagram, we separated the frame from the supports, right? So we break that connection of the frame with supports. And when we break that connection, it means we need to replace that connection with something else. And that something else are the reactions. Okay? For this inclined beam, I didn't break the connection. The beam is still part of the frame. So I don't put any forces there. All right? Okay? That is going to be more clear in the forthcoming examples. Okay? Right. So yeah. So we built the equivalent system force moment with a resultant of the forces and a resultant of the moments. In this case, we have only a moment in the Z component. It's a two-dimensional problem. And now what we need to do is we need to say, in order for this to be in equilibrium, this equivalent system, the resultant of the forces need to be equal to 0 and the moment needs to be equal to 0. If this happens, it means this system is going to be in equilibrium. Yes?
You know after 4.2 times dx?
Sorry?
After 4.2 times dx?
Yeah.
But then minus. Is a minus 4.2 times dy?
You think it should be minus here?
No, I'm just not, no, the one after that. It's minus. Does it say minus?
Oh, this minus and this minus.
Yeah, there's 2 minuses.
No, this is not, that does not become a plus. All right? Still minus, okay? Yeah. Okay, so I do this. It's okay? It's clear now? It's clear now, right? Now it's clear, right? Okay. All right, so these are the equilibrium equations. So because the resultant of the forces is a vector, we will have, look, the first component, x component of the vector, needs to be equal to 0. So we can write here bx minus 2.5 equal to 0. Okay? And the second component of the resultant of the forces, which is this 1, also needs to be equal to 0. So we can say ay minus by minus. So how much is this? Is 60, 110, 120, right? Minus 120. Is this correct?
Yes.
Needs to be equal to 0 as well to be in equilibrium. And so we have two equations so far. Now, the third equation comes from the summation of moments equal to 0. So we can just basically say that all of this and I'm going to do even better than before. I'm going to move this guy from here. Oops. What happened? Oh. Uh-oh.
Yeah. This undo button is very good. Copy. Maybe I need to do something. Okay, so this is the moment equation, which also needs to be equal to 0 to be in equilibrium. Okay? So we have basically three equations for three unknowns, which are bx, by, and ay. Three unknowns for three equations. If we just solve now this system of equations, we get the answer, right? So, for example, from this one, you get immediately bx needs to be equal to 2.5 kilonewtons. Then you need to replace these 2.5 kilonewtons here in bx, and you can solve for by. And once you get by, you replace by here, and you can solve for ay, right? So this is a kind of a very trivial thing to do. We are not going to waste too much time solving this system of equations. The most important thing I want you really to get from this, and trust me, if you get this will be very easy. This model is going to turn into a very easy model for you, I think. The steps are always like this, so please don't ignore the free body diagram. In my opinion, the free body diagram is the most important thing when you solve this kind of problems. Because once you have this free body diagram with all the forces you need to have to solve this problem included, once you have this, you just need basically to build an equivalent system, force moment, and then write the equilibrium equations. That's it. Always like this, okay? So the critical thing for me, and the step where you make most of the mistakes in the solution, is in the construction of the free body diagram. So that's why I want to focus with you on this free body diagram very much, okay? So let's do the second example, this one here. So I can copy this. Any questions on that, or? Yeah, you have? Okay.
When you left out by or bx, when is that? If they come out negative, you have to change the direction on the free body diagram.
Yes. Yeah, the question is, when you solve now this system, if you have any negative value for the unknowns, this means this initial orientation you gave here for these reactions, right? For ay, bx, by, then you need to reverse these directions, okay? For example, in this case, we obtain bx 2.5 positive. It means this initial orientation was correct, okay? If you get, for example, by minus, which you will, probably, we can maybe check that very quickly. No, it's difficult. Anyway, if you get by negative, it means you need to reverse by, okay? Okay, let's do this one now. Okay, let's do this. So you have here this crankshaft, where you have this force P. This force P here, well, is I think is unknown, right? Yeah. So this force P is what you need to calculate. You need to calculate the value of this force P in the handle. Well, you have these two supports at A and B. one, it is said it is a smooth journal bearing, and at B you have a thrust bearing. So what is this? So in order to answer your question, I got this from Ebler's book. I got this from Ebler's book as well. I scanned this. So that kind of support, single journal bearing, as you can see there. And on this column here, on this table, you can see the kind of reactions this support introduces, right? So these reactions means these are going to be what are going to be the constraints to the movement of the crankshaft at that point. For example, if you try to move the crankshaft in this vertical direction, this bearing, this support will not allow that. So it means a reaction Fz. So Z is this vertical axis here, right? So a reaction Fz will appear. If you try to move this crankshaft in the X direction, that will not be possible as well. So then you will have a reaction Fx. Okay? If you want to move the crankshaft in this Y direction, that will be allowed. So it means no reaction in that direction. On the contrary, a single thrust bearing like this one, and you have that in the question. If you try to move the crankshaft in the Y direction, that movement is going to be constrained. So it means you will have an additional reaction Fy in that case that will not allow the movement in that direction. Okay. Another reactions this support introduces are the moments. This moment Mx and Mz. It means this support is constraining the rotation about Z and about X axis. Okay. So that constraint. The constraint of the rotation means we are also introducing a moment as a reaction. Okay? So these are the kind of... so why do you need to do this? Because we need to build the free body diagram. So we need to know what kind of reactions the supports introduce. Okay? So this is something I took from Evler's book. You can see many different kinds of supports. The reactions they introduce, right? Okay. So if you want, we can do a quick analysis here. First, on the supports, we can try to represent here the reactions. So at point A, we have a smooth journal bearing. So it means we will have this, this reaction, which we can call AZ. We will have this reaction AX. And we will have this AZ, and we will have this MAX. Right? That's what we obtained from you agree with me? So that kind of so what I'm trying to do, basically, I'm trying to isolate my crankshaft from these two supports, A and B. Basically, I'm breaking up the connection between the supports and the crankshaft. So it means I need to replace the supports with the reactions. Okay? And if you do that, you get these kind of reactions that are here in green. Okay? Now, for support B, you will have something like this. BZ, BX, and now you will have a BY. This is a thrust bearing, okay? And then you will have MBX, and you will have a MBZ. Look, you don't have any you don't have this in blue, right? Because if you have that moment MBY in blue there, it means if you want to rotate the crankshaft, it will not be possible, right? That's what that moment in blue means. So you cannot have that, right? So these are all the reactions you have, right? You all agree with me or not? So, this is not the most correct way of doing the free body diagram, because I should have removed completely the supports and replaced supports with reactions, right? But because this figure for the crankshaft is a bit hard to draw again, so I'm including the reactions in top of the supports, but for sure you know what I mean, right? Okay, so next step now is going to be so we have everything. We have the crankshaft, we have the external forces, this 400 newtons, and this force P, which is unknown. And we have the reactions, we have a coordinate system, so we have our free body diagram. The next step is the construction of the equivalent system force moment. Yes?
The moments along the x-axis are from 400 newtons. And directed from 400 newtons.
200 newtons, what do you mean?
The reaction along the x-axis, the moments, is that reaction from the 400 newtons?
No, these are moments as reactions. It means if the crankshaft wants to rotate about the x-axis, that support will not allow that rotation.
But is there something that's trying to make it rotate?
Sorry?
Is there something that's trying to make it rotate along the x-axis?
It's good, yeah. When you apply this force P in the handle, right? And when you have that 400 newtons there, look, if you look at that 400 newtons, right? If you multiply that 400 newtons by 350 millimeters, that will give you a moment in the x direction, right? Okay? And that support will react to that moment with that reaction moment at point A and at point B, okay? We are going to see now clearly when we write the equivalent system. Okay, so let's build the equivalent system force moment about point A again, for example. Now, this is a 3D problem. It's different from the previous example. We have these force vectors and moments in all three directions, right? X, Y, Z. So we better work with vectors as we have been doing. So for the resultant of the forces, so let's do this way. So we will have an X, Y, Z component for the resultant. So let's start with this force P that you have here in the handle. That force P, what do you think? Does it have any component in the X direction? Yes. That component should be positive or negative? Why positive? It is opposite with X, right? You see X-axis and the force P, they have opposite directions, right? So it means it needs to be negative. So minus P. What else do we have in the horizontal direction? AX, very good. Plus AX. Anything else? BX. Do we have any force, any other force in the horizontal direction or not? No. Now, vertical direction, what do we have? Sorry? B1? Where is B1? BY. Okay, yeah. Sorry, I understand B1. BY, yeah, good. Yeah. What else? What else do we have in the Y direction? Nothing else. Now Z direction. AZ minus 400. What else? Plus BZ. Anything else? No. So this is the resultant of the forces in our equivalent system force moment. And now we need to work the summation of moments about point A. Okay, so we need to have this, and for the moments, because this is a 3D problem, let's use this expression, the external product of a position vector with a force vector, like we did last week or 2 weeks ago. Okay. So let's start at point A. So we need to evaluate the moments about point A. So our position vectors, they need to have origin. So this position vector here, R, it needs to have origin at point A. Okay? All right. So let's start AX and AZ. These two reactions at point A, AX and AZ. Do you think these two forces produce any moment about A? No. What about MAX? The moment, the reaction moment at about my x-axis. Does it produce any? Yeah. So that moment we need to include, right? Because that is already a moment. That is already a moment. So I'm going to include that moment directly. So that moment MAX is as a component in the x direction only, right? So I'm going to say that moment is going to be MAX in the x direction. You agree with me? What else do I have at point A? I have MAZ is a moment, which is a reaction, with a component in the z direction, which I can also include here in the z component, right? It is already a moment. And these two moments I need to include at point A. So let's say these are the moments, the two reaction moments we have at point A. Now, let's look at this force P on the handle. What is the moment produced by this force P about point A? So I'm going to add the moment produced by this force P. So I need to have a position vector. I need to have a position vector connecting point A with point P, which is this position vector here. Okay, you see? That position vector, this is going to be my position vector R, which I can define this position vector. I need to define an x component for this vector. What do you think? How much is the x component of this vector R? 0, very good. It has no component in the x direction, right? What is the y component? I'm going to use this. We are defining this vector, right? X, y, and z components, okay? So the y component, so you need to look at this y-axis. When you travel from point A to this point, where is the handle, how much do you travel in the y direction? How much? Minus 150 or 250? 250, yes, very good. Minus 250, right? Yeah, everybody understand why it's minus? Because the y component will be opposite with the positive y-axis, right? So we can say we will have minus 250. What about the z direction? Let's see, if you start from A, if you walk in the z direction, you have this minus 200 negative. Yes, very good. So this is my position vector, R. Now I need to do the cross product or the external product of this position vector with my force vector. And my force vector is this force P, which you need to tell me what is the x component of this force P? Minus P. What is the y component? 0. Z component? 0. See? Okay? So, I propose if we do the external product right now, okay? So let me scroll this up a little bit. So let's do this cross product now. So the result of this cross product is going to be 0, 200p minus 250p. Let's check this. X component, we do this cross product, right? Minus 250 times 0 minus 200 times 0, which is 0. Okay? Yeah, but multiplying by 0 becomes 0, right? Y component now, we need to do minus 200 times minus p, which is 200p. Minus 200 times minus p, minus 0 times 0, so 200p. It looks correct to me. Z component, 0 times 0, minus 250 times p. Okay? Sorry? In y direction, you need to multiply by minus 1. Or you just change the cross product. Instead of doing the top left times the bottom right, you do the bottom left times the minus. Right? So we can replace this external product here with this result vector. Okay? Yes? Why is the last one minus? I just deleted. Okay. So you have this, right? 0 minus 250 minus 200. External product with minus p 0, 0, right? Okay? You are saying the z component, right? So for the z component, you need to, you want this component. So you need to do this cross product. 0 times 0 minus 250 times minus p. So this ends up being minus 250p. Okay? Okay, good, good. Yeah, it's negative. I did already 2 times. I don't want to do a 3rd time. Yeah, you will see in the video, okay? I will upload the video. So you need to cross the z component and do the cross product, okay? So it was 0 times something minus 250 times minus p. So minus 250 times minus p. Minus becomes plus, but then we have the minus, right? It becomes minus at the end, I'm quite sure, okay? Yeah? Yes? Sorry, you did speak on.
We're doing it about point A, right?
Yeah.
Why do we fill the translation?
Oh, I didn't finish yet. Yeah, I didn't finish. So we need to continue because this is not the final moment about A, right? We have still more things to do. For example, we have to calculate the moment produced by this 400 Newton about point A. Okay? So we need to have a position vector, which I'm going to define it here. So the position vector we need to have is now connecting point A to this point. Okay? You all agree with me? This is the position vector I need to define. So you tell me, what is the x component of this vector? Minus 250, right? Why is it minus? Because look, this is going to be your x component, which is opposite with x, isn't it? That's why you have minus. Now I need to know the y component. So for the y component, what you need to do, you need to decompose this vector in the y direction. So you get this component here, which has the same direction of our y-axis, isn't it? Yes? Why what? Because we are calculating the moments by doing the external product of a position vector with a force vector. You can do that way as well, and in fact it is a good way to practice at home. You can do the same example by doing that way, okay? But now we are doing the external product between a position vector and a force vector, okay? So the y component is going to be 350, you all agree? And the z component? How much is the z component? 0. Good. And we need to do now the external product of this position vector with this 400 Newton force, which 0 doesn't have any component in x. What about y? 0. Z minus 400. Okay? So we need to do this cross product. Let's do it again. Let's do this cross product. Look, x component. 350 times minus 400. Minus 0 times 0, so we get minus 350 times 400. Right? The x component is this. The y component, now in blue, the y component, we need to do 0 times 0 minus 250 times minus 400, so it will be 250 times 400. Right? And the z component is going to be 0. Okay, if you do the z component, now in black, you have minus 250 times 0, which is 0, minus 350 times 0, which is 0, right? So you get 0 for the z component. You all agree with this or not? Yes? Okay, so if you all agree, we can then replace this . Y is minus. Let's see. Y is minus. Very good. Good. time to do a break, right? We are finishing. We are finishing. Just 5 more minutes, okay? We do a break, okay? Let's just finalize this example. So now everything is correct, right? External product. Good. So let's move this now to here. Oops. What else do we need to do now? Now we need to calculate the moments from the reactions at point B. The moments produced by these reactions about A. So I'm going to add first the moments produced. So these moments, we have MBX, right? MBX, which is a moment already about X. And we have MBZ. So these are the reaction moments at point B. So they are already moments, so I just include these moments. Don't forget, 2 weeks ago we calculated the moment produced by a couple, and we concluded that that moment, it doesn't matter which point we choose to calculate the moment, that moment is always the same. It doesn't change, right? So that's why you can move the moment from point B to point A without doing anything else, because the moment is the same. But we still have to calculate the moments produced by Bx and Bz. So I need to add now. Let's define the position vector connecting point A with point B. We can do this a bit. We can speed up this a little bit now. So position vector RAB is this one here. Okay? This vector only has a component in the y direction, which is equal to 700. You all agree? You all agree or not? 700. So I can say 0, 700, 0. External product with. Now the forces at point B. Well, I have a Bx component in the x direction. This one here. You see? And I also have this BZ component over there. I need also to include. And I also have this By. Okay? So basically I will have something like this. Right? This is my force at point B with Bx, By, Bz. Now if we do this external product here, you can see that your x component is going to be 700 Bz. Your y component is going to be 0. And your z component is going to be minus 700 Bx. Okay? And it is very interesting because, as you can see, for example, this reaction By, the moment produced by this By about point A should be 0 because By is passing on point A, isn't it? And you can see here that in the result, there is no By. Okay? In this result here at the end, you don't see any By there. Okay? So this is just to say that the external product automatically gives you the moment vector. You don't need to worry with anything else. All right? Good, good. So let me replace this one now by this result. Okay, and just to finalize, you can see that we built the equivalent system, force moment, at point A. Now the next step, again, is equilibrium equation. So in order for this system to be in equilibrium, I'm going there. This resultant of the forces need to be equal to 0. This is a vector with 3 components. So we will have 3 equations here, right? You can see one equation here, x components. second equation for the y components, by equal to 0. This one is very easy. Third equation for the z components of the resultant. And for the moment, the same thing. So all these moments, when we add these moments together, the result needs to be equal to 0 if we want the system to be in equilibrium. And from making the moments equal to 0, you will have 3 additional equilibrium equations. So you will have a total of 6 equilibrium equations. Okay? Yes?
What's the difference between the black one on the right and the bottom one? The moment.
Black one on the right.
What are those?
This and this?
No, it's the bottom one and the bottom left. How are they different?
Oh, these two.
Yeah,
These two.
How's the difference to the top one?
Difference to the top one. Which top one?
The black one on the top right. Yeah, that.
This one?
Yeah.
First, the difference is on the reactions, right? Because Bx and Bz, they are forces. Mbx and Bz, they are moments.
So they're both acting.
That is the main difference, right? The moments, they constrain the rotation of the crankshaft, while the forces, they constrain the translation. Okay? But of course, when you have a force multiplied by a distance in perpendicular direction, that will give you a moment as well. That's what we are calculating here now, okay? All right, so you have now a system of equations. You can just solve for the unknowns, and the problem is solved from now on, okay? So I don't want to spend too much time now solving a system of equations. You can do it at home. So I propose let's do a 5 minutes break. Then we come back to solve a very important problem, okay? 5 minutes break. Let's continue, please. So I propose, instead of doing this one now in the morning, we can do this one in the afternoon, okay? I propose if we do now this example, we have more or less 30 minutes. I propose we do this example, which was the example from last year exam. Okay? And I think I already discussed with you the format of the exams, right? In week 1, no? No? Are you sure? So basically you will have, in the exam you will have 4 questions. You need to do 2 out of 4. Okay? 2 questions out of 4. Which is very good for you because you have options, right? So, this was in last year exam. Let me change the lights because... Okay, so, you all know this mechanism, right? You all know this mechanism, right? So, you have this pump where probably you use this for your bike, right? So, the thing is that you are putting a 250 Newton force. You are putting a 250 Newton force at point A with your foot. Okay? What else? There is a spring here, this spring S that you see here. This means when you put that force 250, this spring here will react with a moment. Okay? And that moment is given in the question. Look, 3 Newton meter moment. And this moment is being applied on this member OBA. Basically, it's this member here, right? OBA. You can see, right? And that moment is being applied at point O in this member OBA. Okay? What do they want to know? Well, they want to know, for example, imagine that you are working in a company. This company makes this kind of pumps, foot air pumps, and your boss comes to you and say, "Oh, okay, so please design this cylinder. You have this cylinder here, right? Pneumatic cylinder. Design this cylinder for this pump, assuming that a maximum force of 250 newtons are applied at point A. So what should be the force in the cylinder? Okay? What is the force in the cylinder? All right, another important thing, and I just had one of your colleagues here asking for the previous example, the crankshaft. Because, for example, the crankshaft, crankshaft is rotating, right? So the analysis we did before for the crankshaft was for a particular instant of that rotation of the crankshaft, right? And the moments we calculated was for, imagine that you have the crankshaft rotating and you just froze that rotation at this instant, and then you do the calculations for this instant, right? And then for this instant, with this configuration, you calculate the force P, which, by the way, I had some colleagues saying this force P was 500 newtons. For this example, for this pump, is basically the same thing, right? When you are, putting air in the tire of your bike, for example, you are pumping with your foot, right? And there are different configurations for this. But the analysis I want you to do is for this time instant. For this configuration, where you have these dimensions, okay? For this configuration, with these dimensions, for this instant, what should be the force in the cylinder? Cylinder BD. So you can see BD is this cylinder here, okay? We are going to ignore this second part of the question. Okay? What I want you to calculate now for this model is just the force in the cylinder. And why did I decide to choose this example for today? Not because it was an example from the exam, but because this example will show you the importance of the free body diagram again. Right? You have here many different structural members. You have this member OBA, okay? You have this. What else do you have? You have this member OD, okay? What else? You have the cylinder BD, right? And you have the entire pump, which is basically made of this, right? Okay? So what I'm showing you, there are many different possibilities for different free body diagrams. I can do the free body diagram for the entire pump, or I can do the free body diagram for only member OBA, right? Or I can do the free body diagram for the cylinder only, BD. For example, let's do the cylinder, BD. If I do the free body diagram of the cylinder BD, so I will have here point B, I will have here point D, okay? So in order to do the free body diagram of cylinder BD, I need to isolate the cylinder for the entire pump, okay? So I need to break the connection of the cylinder at point B and at point D. And when I do that, I need to basically replace that connection with the reactions, like we did in previous examples, right? When we remove for example, the crankshaft from the support, we replace the support with the reaction. Same thing here. If my free body diagram is the cylinder, if I am separating the cylinder from the entire pump, so I need to replace the connections at B and D with the reactions at B and D, okay? And for doing that, I'm going to include the reactions at D. So a reaction in the vertical direction to my cylinder BD, and the reaction, so I will call this dy, this dx, and I will have a reaction at point B, by, and bx. Okay? So, of course, I am assuming this is my x coordinate system and this is my y coordinate system, right? I can do this, no problem. So, and now look at this. Look what I'm going to do now. So this is my free body diagram. So let's assume, for example, this length. You can calculate the length of the cylinder from the figure, but for now, let's just assume this length is a generic length, L. Doesn't matter. And what I'm going to do now is, okay, this cylinder needs to be in equilibrium. Like I told you last week, everything needs to be in equilibrium. It doesn't matter if it is the entire pump, or if it is only the cylinder, or if it is member OBA or member OD. It doesn't matter. Every single free body diagram that you have needs to be in equilibrium. In equilibrium means summation of forces equal to 0, summation of moments equal to 0. So let me do summation of moments about point B need to be equal to 0. This is my equilibrium equation. Let's see what happens, okay? This is a very important thing, please. Which moments do I have about point B? So let's start with these reactions By, Bx. Do they produce any moment about B? No. Now, reaction Dx. Does it produce any moment about B? Yes? How much is it? No, right? This force, look, this force dx, if you extend, is passing on point D. So the distance in the perpendicular direction is 0, right? So no moment. What about my reaction dy? Does it produce any moment about B? Yes. And that moment is the length, which is L, times the force, which is dy, isn't it? That's all I have for the moments about B, isn't it? Now, the equilibrium equation tells me these moments needs to be equal to 0. So, this needs to be equal to 0. And look at this now. This is very, very important. What we have here is, the solution of this equation you have here is L equal to 0 or dy equal to 0. Is the only option we have, right? Isn't it? Do you think L equal to 0, do you think this is reasonable? No, L equal to 0 means no strut, right? Or no cylinder, BD. So the only really option for this member to be in equilibrium is if this reaction dy is equal to 0. If you do this analysis, exactly the same analysis for summation of moments about point D, you get, so if you do summation of moments about point D equal to 0, you get LBY equal to 0. You get also BY needs to be equal to 0. All right? So the conclusion is a strut like this, cylinder BD, where you have two hinges, one at point B, one at point D, a strut in these conditions with these supports means that these perpendicular reactions, dy and by, they need to be equal to 0. Otherwise, this strut is not in equilibrium. And the conclusion is, when we have a strut in these conditions, the only reactions we will have are bx and dx. But we also know that, so I need to find some space, so let me delete this now. We also know that if I now use the summation of forces in the x direction equal to 0, which is my other equilibrium equation I have, my conclusion is dx minus bx needs to be equal to 0, isn't it? Which means my dx equal to bx equal to my force in the strut. Okay? And I know that this force in the strut needs to have the direction of the strut. And this is a key thing to solve this problem. This is the key thing to solve this problem, okay? So please keep this in mind. If you have a strut with two hinges at the ends, at point B and at point D in this case, the force or the reactions are equal to the force in the strut, which needs to have the direction, the longitudinal direction of the strut. Okay? And why do we need this to solve this problem? So we didn't solve this problem yet. We don't know yet how much is this force F in my strut. I can say this is FBD, the force in my strut BD. I don't know yet how much is this force. But in order to solve this problem, what I have to do is I'm going to copy this. What I'm going to do is, I'm going to do another free body diagram for a different component. I'm going to do the free body diagram for this component, OBA. Okay? So in order to do the free body diagram for this component, I'm going to break up the connections of this member, OBA, with, first, the foot, the cylinder BD, and this OD member as well, right? So basically what I'm going to do is I'm going to isolate. So this is point O, this is point B, this is point A. So I'm going to isolate this member OBA from the entire pump. What do I need to represent? Now, I need to represent all the external forces in this member. One is the force of the foot, right, which is 250 newtons. So I can represent it here. 250 newtons. You know the direction of this force because this angle is 15 degrees, okay? What else do we have? Now, I separated at point B, I removed the connection of the cylinder BD at point B. So it means I need, what did we conclude for the cylinder BD? I'm going to write it here. So this is my point B, this is my point D. We concluded that this cylinder will have a force in the longitudinal direction of the strut, right? That's what we concluded before. This is my force FBD, which is equal to this, FBD. Okay? And now, why is this important to solve this problem? Because look at this now. This force is the action of my member OBA onto the cylinder, okay? Onto the strut, BD. So basically, my member OBA is pushing this cylinder BD up and left, right? With this force FBD. What is going to happen is, this cylinder BD will react onto my member OBA with the same force but in the opposite direction. Okay? So this FBD that you have here in our member OBA, we know completely the direction of this force because it needs to have the direction of my cylinder BD. Okay? Which we can easily calculate. For example, look at this. You have here this rectangular triangle. This height here is how much? 85 minus 25, so this is 60. And this length here is how much? 225 minus 25 is 200, right? Isn't it? So if you calculate this angle here, alpha, you can say tangent of alpha is going to be equal to 60 over 200, which gives you alpha equal to 16.7 degrees. I have this. So basically, I know this direction because this angle here is 16.7 degrees. Because I know this force needs to have the direction of my strut. That's what we concluded here, right? The force needs to have the direction of the strut or the cylinder. So basically this force here at point B in my member OBA is going to be only one unknown, which is FBD. because we know the direction of this force. It makes 16.7 degrees with the horizontal direction. Okay, so this is only one unknown. But we need to continue because we also, in order to isolate, remember, OBA, we also remove the connection at point O. So we need to represent, so at point O we have an hinge and we have a spring there. So we need to include what? The effect of the spring, which, as the question said, it was a 3 Newton, I think it's 3 Newton meter, right? Yeah, we have a moment of 3 Newton meter. We can put like this, 3 Newton meter. Okay, this moment basically is the effect of the spring. So when you push with your foot, this spring will react with this 3 Newton meter moment at point O. And now, because I separated the connection at O of this member OBA from the rest of the pump, I need to include the reactions at O, and that reactions are, this is an hinge, so I will have OX and OY. Okay? This is a two-dimensional problem. OX and OY. All right? Look at this. I'm going to delete this now. So this is my free body diagram. So this can be my X direction. This can be my Y direction. Okay? So this is my free body diagram for this member OBA. So far we did 2 free body diagrams. One for the cylinder, the strut, one for this member OBA. And before you start doing the calculations, what I recommend you to do is check first if you have enough equilibrium equations for the unknowns. So let's do that for this example. First, this is a two-dimensional equilibrium problem, so we will have 3 equilibrium equations, right? Which are summation of forces in the X direction equal to 0, summation of forces in the Y direction equal to 0, summation of moments in the Z direction equal to 0. These are my 3 equilibrium equations. And now let's count the number of unknowns that I have. I have FBD, okay? I have OX, and I have OY. That's it. 3 unknowns. OX, OY, FBD. So 3 unknowns for 3 equilibrium equations. It means this free body diagram will work, will give me the solution for this problem. Okay? If for some reason you don't have enough equilibrium equations, it means you need to do another free body diagram. Okay? Now, I can tell you now what happens if you, so I can copy this. Copy, paste. So what I can say what most of the students did when they tried to solve this in the exam was they didn't do this analysis for the strut. So instead of doing this FBD, what they have done was they basically included a BX and BY. Okay? And what happened was, if you do this, at the end you will have 4 unknowns. 1, 2, 3, 4. And you have only 3, so basically you will have, in this case you will have 4 unknowns, for only 3 equilibrium equations. And then it means they cannot solve the problem. Okay? So what do they have to do in order to solve this problem? Well, in order to solve this problem, if they want to use this approach, they can do it, but then they need to do another free body diagram for the strut, right? For the cylinder, BD. And then they need to say at point D, okay, so if I have this BX, a force to the right, so in the strut, it's going to be the reaction which is going to be pushing to the left. So you need to basically put the same BX here, but pushing opposite with this BX, right? Action-reaction, or Newton's third law. Same thing for By. If on the member OBA, By is upwards, in the strut, the reaction should give you By downwards. And this is critical. If you don't do this action-reaction, you are violating Newton's third law, and everything comes wrong at the end. Trust me. And now at point D, they also need to do this. These reactions at point D. So let's see how many reactions you have in total. You have 4 here. So you have OX, OY, BX, BY. So this BX and BY, they are on the strut BD, they are the same. So this and this, they are the same reactions as before. So they are not new reactions. But you have these new reactions. Now, you have here 2 different free body diagrams. You have this one that will give you 3 equilibrium equations. And you have this one here that will give you also 3 equilibrium equations, right? Right? So 2 free body diagrams here. Each of these free body diagrams will give you 3 equilibrium equations. So you have a total of 6 equilibrium equations for 6 unknowns. And now you can solve the problem. So basically this second free body diagram will lead you to this same conclusion we obtained here for our strut, okay? And then you can now solve this. So if you want to adopt this approach, you will spend much more time in your exam because you have to do 2 free body diagrams, but you can still get the solution at the end, the same solution, okay? So this is why I think the free body diagrams is extremely important, and because calculating moments and putting the forces in vectorial form and then writing the equilibrium equations, this is quite trivial, isn't it? The most difficult thing is you guys to understand how you should put the reactions, the action-reaction or Newton's third law. If you violate Newton's law, trust me, that is very, very bad. You don't want to do that, okay? So Newton's third law says for every action there is a reaction. And it's quite easy to understand. If I'm pushing this wall to the right, the wall will react in my hand, pushing my hand to the left. So at the end, my hand is in equilibrium, isn't it? Action-reaction. Right? For example, if I put my hand on the wall, okay? So if my hand, okay, if I now isolate my hand and the wall, okay? So what is going to happen? Look at this. The force I am applying on the wall is a force in this direction, let's say F, right? The wall will react in my hand with the same force but in the opposite direction. Okay? So at the end, I will have here summation of forces is going to be equal to 0. So my hand is in equilibrium when I'm pushing the wall, right? Action-reaction. So if for some reason you decide to do something like this, if you decide to say, okay, I'm pushing the wall to the right with this force F, and then the wall is reacting in my hand with the force in the same direction, this means my hand should go through the wall, right? Isn't it? So doing this, you are violating Newton's third law, and everything comes wrong after this. There's nothing I can do. Not only me. There's nothing you can do, right? Everything comes wrong. So this is a critical thing. And I think in this example, this shows very well how this, how you should play with free body diagrams and with Newton's third law to get this. Because, for example, in this example, if this Bx I put here, if I put in this direction, trust me, this problem comes wrong at the end. You cannot solve it. It's quite critical, okay? So just to finalize, don't forget, guys, there are a lot of books in the library, many different authors, with many, many, many examples. We are going to do tutorials. The more you practice, the better for you to understand these kind of things, okay? You need to practice, all right? Yes? Maybe you can come here, we can start. Yeah? So, in the morning we were doing this example from last year exam. We didn't finish, so we agreed that the free body diagram of this member OBA with the reactions OX, OY at point O, and also the force FBD for the force that is going into the cylinder, which needs to have the same direction of the cylinder. And then we have the moment produced by the spring, 3 Newton meters, and we have the 250 Newton force that is being applied at point A. Right? So this is our free body diagram, and we concluded in the morning that we have 3 equilibrium equations. 3 equilibrium equations because this is a 2-dimensional problem for 3 unknowns, which are OX, OY, and FBD. So we are ready to go. So we will continue now this exercise. So we will build an equivalent system. We will build an equivalent system force moment at point O, for example. Okay? Let me just increase a little bit this figure so we can get dimensions, because we are going to need the dimensions now. So let's build the equivalent system force moment about point O. So the first thing we need to build is the resultant of the forces. X component of all these forces. Which X components do we have? Sorry? Sorry, which X components do we have? OX, yeah. OX, what else? FBD times what? Cos 16.7, good. Plus 250. Sine or cosine? Sine. 15 degrees, right? Do we have anything else in the X direction? Do we have or not? No. What about Y direction? OY? What else? Positive or negative? Minus 250 times cos 15, good. What else? Minus FBD. Good. Very good. Now, summation of moments about point O. So the Z component only. Right? So in a 2-dimensional problem, again, I keep repeating this. In a 2D problem, the moments will have a component in the Z direction only. So, moments about point O. You tell me. OX and OY. Do they produce any moment about O? No. What about these 3 Newton meters? The moment produced by the spring. Should I include or not? Yes. So we have here, so that moment is anti-clockwise in the figure, right? So we have 3 Newton meters, should be there. Now, looking at this force FBD, force that goes to the cylinder, what is the moment? So you can do this, for example, in this way. One is to decompose. You can decompose this force FBD into an horizontal component, which is this one in green, and into a vertical component, which is this one also in green here, right? You all agree with me? Remember the first week we talked about addition of vectors and the composition of vectors in two different directions, right? Now I'm decomposing this vector FBD into two directions, which are direction X, direction Y. So you can say, for example, this component here, how much is it? Is FBD times, right, cos 16.7, while this component here is FBD sine. You all agree with this or not? Yeah, so now for the moment it is about point O. It is easier to use these two components I have there in green instead of using FBD, right? Well, if you want to use FBD, you can always do the external product of a position vector with the force vector. You can also do that. But we are doing a different approach now. So let's start with this. In fact, I'm going to move this component I'm going to move the horizontal component to this position here and then, okay? All right, so let's start with this one. What is the moment produced by this horizontal component, this one here? FBD sine 16.7. What is the moment produced of this component? About point O. It's going to be first clockwise or anti-clockwise? Clockwise, so negative, right? Minus. Now, what is the length I need to consider? I need to consider this length, right? From here to here, right? You all agree? How much is this length? 85. You all agree with this? So minus 85 times the force, which is FBD sine 16.7. All right? You are all following this or not? Now, let's do the analysis for this component of the force, this one here. First, moment will be clockwise or anti-clockwise? Clockwise. So minus again. The distance I need to consider is, this is the direction of my force, so I need to consider this distance, right? Which is? How much is that distance? 25, right? So minus 25 times FBD cos 16.7. All right? So that moment produced by FBD about point O is done. But we still have to consider now the moment produced by this 250 about point O. So we can do a similar approach. We can decompose this force 250 into a horizontal component, this one, which is 250 times what? This horizontal component here, 250 times cos 15 or sine 15? Sine 15. And we will have also this component here. And this component is 250, now cos 15, right? You all agree with this? And now we do exactly the same thing. So if we look at this component first for the moment, about point O, that moment is going to be clockwise or anti-clockwise? Clockwise or anti-clockwise? Clockwise. The distance I need to consider is this one here, So this is the line of the force. The distance I need to consider is this, which is, how much is it? 185, right? So minus 185 times the force, which is 250 sine 15. And now the last term I need to consider for the moment is the moment produced by this component. Moment is going to be clockwise or anti-clockwise? Clockwise, so minus the distance I need to consider now is this one from here to here, right? Which is how much? 150? 125 plus 25, isn't it? So minus 150 times that force, which is 250 cosine 15. And the last one I need to consider for the moment is this component here. Again, moment is going to be clockwise, negative. And the distance I need... Oh yeah, I've already done this. Sorry. So that's it. These are all the moments we have about point O. And then, so these are the moments we have about point O. This is the resultant of the forces. What we have to do now is, so I'm going to copy this to another slide. Okay? So what we have there is the resultant of the forces and the moment. Yes?
Why is it 85 sine?
85, this one here?
Yeah, why is it 25?
So let me see if you are talking about this one.
Yes.
All right, so let's check this again. So this is FBD sine 16.7. So is this component here, right? Right, so this component, the moment about A, the distance, so this is the line of the force, right?
Yeah.
The distance you need to consider is this one, you agree? Which is 25. Okay, good. And, okay, so this one is 25. Let's check this one now. Let's check the moment produced by this one. So the moment produced by this one, the distance I need to consider is this one here. This is 85, right? Yeah, so okay. I know what happened. So this should be 85 now, correct? So let me fix here as well. So we need to have here 25. And we need to have here 85, right? Okay, good. What else? Anything else? Okay, so in fact, I just wanted to check if you guys are paying attention. No, of course not. It was my mistake. I'm sorry for that. But I fixed it. All right. Now let's continue. So we have here the resultant of the forces. We have the moment. So we have the equivalent system force moment. In order for this to be in equilibrium, the resultant of the forces need to be equal to 0, and the moment needs to be equal to 0, right? Okay? So we will have three equations here for three unknowns. The three unknowns are OX, OI, FBD. Okay? So you solve this system of equations, three equations for three unknowns. You get the force in the cylinder, FBD, which is the answer to this question. All right? Okay? All clear now? Can we move to the other example, or is there any questions? Can we move? So let's do the last example in today's lecture, which is this one. So I'm going to copy Okay? All right. So let's do this example and we finish. Come on, just a little bit more. Otherwise, I have to be yelling here. It's not good. Please silence. So let's do this last example and we go. Okay? Yeah, we go. Well, we finished the lecture. I still have more today, but you might be free. I don't know. All right. So this example, you have this structure here. So basically you have a tubular frame. So you have these 2 kilonewtons. You have these 2 kilonewtons applied here in this point. What else do you have? Well, you have this cable connecting point C with point D. You see this cable here. And then the supports, basically you have this support here at point A, which is basically an inch in 3D. So basically this inch, we are going to see what kind of reactions it will introduce. And you have this other support here at point B. We are also going to see which reactions it introduces, okay? So what is the question? So you have this load, we talk about it. Now, they also say here, rotation about a line from A to B is prevented by the cable CD. The cable is stable, the frame is stable in this position. They ask us to neglect the weight of the frame. Of course, this frame, they have some mass, they will have some weight, but basically they are saying, comparing the weight with this force of 2 kilonewtons, we can basically neglect the weight. That's what they are asking us to do. The question is, calculate the tension in this cable, CD. So basically they want us to calculate the tension in the cable, CD, and then they want us to calculate the reaction at the ring. So this is the ring. They want us to basically to get the reactions at support B, and they want us to get the reactions at support A as well. Okay? So basically the question is, calculate the reactions at support and the force in the cable. Okay? So, first thing to do, again, free body diagram. So we need to isolate this body from the support. There is one important thing we need to do here because we want to get the force in the cable. So basically, we will have to cut our cable somewhere. You see? I will have to cut our cable so that by breaking the connection on the cable, I can replace that connection with the tension in the cable or with the force in the cable, right? So I will need to cut the cable And I will need also to separate the supports. Basically, I will need to separate this frame from the supports. So I will need to break up the connection at this support, at this hinge, at point A. And I will need to break up the connection of the frame with support B. And then if I do this, imagine you have a scissor, you are there cutting these connections, you can then isolate your frame, which we can represent here, something like this. Okay? And then look at this, because I did cut my cable CD, here, right? So I need to replace my cable with this tension, T, on the cable, which has the direction of the cable, right? That's what we have been doing so far. When we separate the frames of the structure from the supports, we replace the supports with reactions. For a cable, it's the same thing. I'm separating my structure from the cable, I'm cutting the cable, so I need to replace the cable with the reaction on the cable, which is the force on the cable, okay? Which is also always a tension force, not a compressive force. Cables, they only carry tension forces, okay? Now, what else do we need to include in our free body diagram? Well, I need to include my 2 kilonewtons force. You all agree with me? What else do I need to include now? Now I need to look at the reactions at point A and point B. So let's start with point A. At point A, it is an hinge, right? So an hinge means if this is my that column you have there, if I try to rotate about point A, that is possible, right? Look, point A does not move, it's fixed, but the rotation about point A is possible. Hinge tells us something like this, right? You can see it from the pencil here, right? What I'm doing. I'm rotating the pencil about point A, right? So that rotation is possible. So it means no moments as reactions, because the rotation is allowed to happen. But on the contrary, if I try to move point A horizontally or vertically or in the other direction, that hinge does not allow that translations to happen. So it means the reactions I will have are going to be one reaction in the y direction, one force in the y direction, one force in the x direction, and one force in the z direction. Okay, and that's all the reactions I have at point A. I don't have any moments because the hinge allows the rotation about A. Okay? Now, point B. Point B. Point B, we will have. So if I try, I'm going back to this figure here, it's easier. If I try, imagine for example, if I try to move point E in this direction, in the x direction, do you think that support will allow me to do that? No. So it means I need to include here a reaction, let's say, Bx. Okay? If I try now to move point B, if I try to move point B in the z direction, in this direction, do you think the support allows that movement? No. So it means I need also to include here a reaction Bz. If I try to move point B in the y direction, in this direction, that movement is possible, is allowed, okay? So it means no reaction. Whenever a movement is allowed, it means we don't put any reaction over there. Same thing, rotations are allowed for this kind of support. So the only two reactions we will have, at point B are going to be these two, okay? So In our free body diagram, we isolated this tubular frame. We included the force in the cable T. We included the external load, 2 kilonewtons. We included the reactions at support A. We included the reactions at support B. So we have our free body diagram completed. Of course, we need to have the coordinate axis. This is my Z direction. This is my X direction. And this is my Y direction, right? And then we are ready to now obtain the equivalent system force moment. That's what I'm going to do now. Before, I need to find some space here, so let me shrink this a little bit. Okay? What about that? Not bad. Sorry? Which moment? In the support. That's what I was saying. Point A, this is point A, okay? Point A here. The frame is allowed to rotate about point A. It is an inch. If the rotation is possible, is allowed, it means no moments as reactions. Only when the rotations are constrained, you put a moment as reaction. In this case, the rotations are allowed, okay? Support B, yeah, rotations are also allowed, about B. Yeah, I understand your question. What you are saying is that for example, if I try to rotate, so depends on the width of the support. Let me see how can I do it. If you have a support B like this, as wide as this one, that rotation might be constrained. But this ring, that's why it's called a ring. This width is very tiny, so it means it can rotate about that point. Okay? Yeah, so assume the rotation is allowed. So it means there is no moments as reactions, okay? This is different from the bearings, from the previous examples we did in the morning. The bearings, they have that width long, so that the rotation is not allowed because of that wide support, okay? But here is different. All right. Now, equivalent system. So let's calculate the equivalent system about point A. Is it okay? Or you want a different point? Any point is okay. I think point A is fine because these three reactions, AX, AY, AZ, they will not produce any moment about point A. We can simplify a little bit our calculations, okay? So let's start with the resultant of the forces. This is a 3D problem. This is a 3D problem. Which components we have in the X direction? You tell me. AX. What else? Minus BX. What else? We might have some component for the cable, force in the cable T, right? So this force in the cable T, I want to define this force vector T by doing this. T, which is the magnitude, times a unit length vector giving me the direction of this force T. I want to characterize this force in the cable, this tension T, in the following way, okay? We discussed this in week 1. So this component here basically is the norm of T, or the magnitude of that force, or basically is the force in the cable. While this component here, the norm of this lambda is equal to 1, so it's a unit length vector. So unit length vectors, we know that they only give us the direction, nothing else. Okay? So I need to calculate this unit length vector, lambda. That's what I want to do with you now. So in order to do that, we will define this vector connecting point C to point D. Are you following me? Maybe I can scroll down a little bit. Yeah. We are going to define this vector connecting point C to point D. So this vector, CD, will not be a unit vector, right? But it will give me the direction of the cable. And then I just need to divide this vector by its norm to get a unit length vector, to get my lambda vector, okay? We are going to do that, don't worry. So let's define first this vector CD. I'm going to write here. So don't forget CD. X component. So you can do, before we do this way, you can do CD is equal to point D minus point C. Okay? Okay, what is the x coordinate of point D? Minus 1. You agree with me? So this point D here, this point D, okay? What are the coordinates? Minus 1. In the y direction? I think in the x direction is minus 1, isn't it? Is this one here minus 1, right? No, I'm talking about the coordinates of point D, not the component of vector CD. They are different things. Okay? I think this way is less confusing for you. So coordinate of point D in the x direction is minus 1. In the y direction is this 2.5, isn't it? In the z direction is 0. Right? You all agree with me? Now, minus coordinates of point C. This point here in the top. What is the x coordinate? Minus 3. What is the y component? Why is it 0? Because it is 0, yeah, you're right. Yeah, sorry, I was thinking. So point C, y coordinate is 0. Now, z coordinate, 6. Now, if I just subtract these two vectors, okay? So I have, for the x component, I have minus 1, minus 3, so minus 1 plus 3 makes plus 2. 2.5 minus 0 is 2.5. 0 minus 6 is minus 6, right? So these 2.5 minus 6 are the components of my vector CD. You all agree? It looks correct to me. Okay? So, let me just move this. Let me move this up. This gives me the direction of CD of the cable, but this is not a unit vector. So I need to calculate now the norm of CD, which is square root of 2 square plus 2.5 square plus 6 square. How much is this square root, please? Someone can do the calculation for me? But what is the final result? Can you do the square root? Sorry? 618? 618. 0.18. 6.18. Is this correct?
No, 6.8.
Is this correct? Okay, good. All right. Now that we have this, we can say, look at this now. We can say my lambda vector, which gives me the direction of my cable CD, is going to be this vector CD that we just calculated, divided by its norm. So when I divide the vector by its norm, I'm basically normalizing the vector, or making the norm of the vector equal to 1. Okay? So it means I need to divide all the components of my CD vector by 6.8. So I will have here 2 over 6.8, 2.5 over 6.8, minus 6 over 6.8. Okay, can you please tell me how much is this? The first one, 2 over 6.8. How much is it? 0.5? 0.29. 0.294. What about the second component? 2.5 over 6.8. 0.368. The last one. 6 over 6.8.
Minus 0.882.
882. Good. Okay. Now, we are almost there. Let me just find some space here. Okay? Now look at this. I'm going to write my T vector, my force in the cable vector, as being equal to the norm T times the lambda or unit vector, which is this one here. I'm just going to copy and paste here, okay? Or if you want, you can write this vector as being something like 0.294t, 0.368t, minus 0.882t. Okay? And I have my force in the cable, the vector, force vector in the cable, completely defined in terms of norm, magnitude, in terms of direction. I have the components in the x, y, and z direction of this vector. And how can I now use this? How can I use this now to calculate the resultant? So going back here to the resultant of the forces. How can I use this here in the resultant of the forces? So I basically just need to add, for example, in the x direction, I need to add this x component, right? This x component. So I'm going to add here plus 0.294t. Okay, you see? In the y direction, now this component here in the y direction, so I will have 0.368t is the component in the y direction of my tension in the cable. But I have other forces in the y direction, right? What else do I have in the y direction? AY. What else? 2 kilonewtons plus 2. What else? Anything else? That's it in the y direction. Z direction, I have this component of my force in the cable. What else do I have in the Z direction? AZ plus or negative or positive? Minus AZ. BZ, right? Plus BZ. Anything else in the Z direction? No, that's it. Okay? All right? So this is the resultant of the forces. Of course, now we want this to be in equilibrium. We will say this needs to be equal to 0. Then we have our first three equilibrium equations. But it's not enough, right? Because look, we have there AX, BX, AY, T, AZ, BZ. So we have many unknowns for only three equilibrium equations. Not enough yet, but we didn't finish. What do we have to do now? Moments. We need to calculate the moments about point A. Right? So I'm going to delete this, I need space. Let's keep this vector because we will need this vector. Let's keep it here somewhere. This is my vector t, don't forget. Okay, so let's work the moments. So, summation of moments about point A. Again, we are going to do the moments by doing the external product. In a 3D problem, it's much easier, trust me. Okay, let's start with the moment produced by these 2 kilonewtons. Moment produced by these 2 kilonewtons about point A. So we need to define the position vector first. We are calculating the moments about point A, so the origin of the position vector needs to be located at point A. Alright? So, for this force, the position vector that I need is this one here. For the 2 kilonewton force, when you are calculating the moment produced by this 2 kilonewton about point A, you need to define a position vector connecting point A and the point where the force is applied. Okay? So we need to define this vector. X component. Let's do it. We need to speed up a little bit. X component of this vector here in red. What do you think should be the X component? So you need to decompose this vector in the X direction, which will give you this, right? The X component should be 2.5, right? So let's write here 2.5. Now, Y component, you need to decompose this vector in the Y direction. 0, very good. Z component, 6. You see, you are already mastering this. That's good, that's very good. Now we need to define the force vector. This 2 kilonewtons is a force with component along the Y direction only, right? So this force should be 0, 2, 0. You agree? And then we just do the external product now. So I'm going to speed up the external products now. So we have in the Y direction we have minus 12. In the Y direction we have 0. In the Z direction we have 5. All agree with this? Let's move this one here. So this is the moment produced by this 2 kilonewton force. We completed. Now let's focus on the moment produced by the force in the cable, T. What is the moment produced by this force in the cable about point A? So again, the same procedure again. We need to define the position vector. Which position vector is this that we need to define? Sorry. We need to define the position vector connecting point A to point C, which is point C. As you can see, the point C is where the force of the cable is being applied, right?
Yes.
So we need a position vector connecting point A to point C. As always, point A, why? Because we are evaluating the moments about point A. That's the reason. Why then point C? Because it is the point where the force is being applied. Is being applied at point C. And now this vector, we do the same thing. We need to define the X, Y, and Z components of this position vector, starting with the X component, minus 3. Y component, 0. Z component, 6. And now the force vector. The good news about force vector is we already calculated force vector. Right? So I can just basically take this force vector T and move it. Before I do that, let me delete this. Okay? And now I just need to do the external cross product, which will give me minus 6 times 0.368t is the x component. Y component is going to be 6 times 0.294t minus 3 times 0.882t. Z component is going to be minus 3 times 0.368t. This is the result of my external product, which I can just, which I can just now replace here. We are almost there. We are finishing. The last one we need to do now is the moment produced by the force at point P. The moment produced by that force vector about point A. So what we need now to consider, the position vector we need to consider, we go back here, is this position vector connecting point A with point B. Okay? Connecting point A with point B. So I'm going to continue here below. Position vector, x component. How much is it? 0, right? You all agree? X component is 0? Why is it 1? That is the y component. X component, it needs to be the component in this x direction, right? Of this vector. If you project this vector AB in the x direction, you get 0. Isn't it? Look, that's what this means here, right? This dashed line you have there means this point B basically is a point located in the plane YZ. Isn't it? The x component is 0. Right? So 0 for the x component. Y component, like you said, no, it's not 1. Sorry, it's not 1. Y component needs to be this component, right? This is my y component, which is 4.5, yes. I said 1 before, so I apologize. So 4.5. And the z component is 6. Force vector is very quick. Bx, 0, Bz. Correct? So let's do this cross product. We have 4.5 Bz. Then we have 6 Bx. And then we have minus 4.5 Bx. Is this correct? So I can replace my external product with this final result. And then I think we have everything. So it means we have all the moments about point A. We just need to say this summation of the moments needs to be equal to 0 again, to be in equilibrium. And then we have 3 additional equations, which makes a total of 6 equilibrium equations. Let's count the number of unknowns that we have. Let's count that. So we have AX, BX, AZ makes 3. Then BX and BZ, it makes 5. And then we have the tension T in the cable. It makes 6. And that's it. So 6 reactions or 6 unknowns for 6 equilibrium equations. We just need now to solve this system, 6 equations for 6 unknowns, and we get the answer. Basically, the answer is the answer to this question. So if we solve this system of equations, we get the tension T, we get the reactions at the ring, which is Bx and Bz, and we have the reaction components at A, which are Ax, Ay, Az. Problem solved. Okay? Is it clear or not? Okay, just to finalize, my recommendation to you is you will have these videos in Panopto. You can review the videos if you want, but nothing replaces your study. My recommendation is go to the library. There are many books there, different authors. They all have many, many exercises. We are going to do more exercises in the tutorials next Thursday, but the more you practice, the more used you get with these kind of things, okay? Yes? Reaction where? AY. Yeah, it's here. It's not 7, it's 6. I did Bx twice, yes. Sorry, I did Bx here one time, and then I counted here again, sorry. So it's 6, look, it's very easy. Look, hold on. You have here, if you look at the free body diagram, you have Ax, Az, Ay, makes 3, Bz, Bx makes 5, and then you have the tension makes 6, okay? You have 6 unknowns for 6 equilibrium equations, not 7 unknowns, right? Okay, so see you guys Thursday, right? Yeah.